So we have a quiz every Tuesday, and I'm testing you to see if you know the material so I can help you out and you know what you need help in. Okay? So don't stress out about it. Alright, so let's go over this one. Okay, so if you read the problem, for the given force shown in the figure, the resultant force is that, and the resultant moment is that at point O. Determine the location of the resultant force with respect to point support O, and draw a free body diagram showing the locations. So what kind of problem is this?
Force location.
Force location problem. So it's an equivalent system problem, and there are two different types of equivalent system problems. One is force location, and the other one is force moment. In both equivalent system problems, what do you need to do first? We're going to go around. Let's go in the back. John, for equivalent system problem, what's the first thing you need to find? You could pass.
Yeah, pass.
Okay.
David. You find the resultant force.
First, find the resultant force. And do we need to find it?
No.
No, they gave it to us. Cameron, what's the second thing you do? Find the resultant moment. Find the resultant moment. And do we need to calculate that?
Nope.
No, because it's also given. Why? I just wanted it's a 10-minute quiz. I didn't have you calculate that. Those things you've already done many times. If it's a force location problem, what's the next thing we need to do? Daniel. Find the perpendicular distance. So how do we find the perpendicular distance? What is it equal to?
Magnitude.
Daniel? The moment divided by the force. So what's our moment here? 15,928, right? Inch pound. Mike, do we need to do something with the force, or should I put it in vector form here? I need to find the magnitude. So how do I find the magnitude of the force? 528.6 squared, 260.3 squared. Does anybody remember what number they got?
589.2.
582?
589.
How does that sound?
Yeah.
Okay. So we got the force in vector form, so we had to turn it into a magnitude. And then we put that number up here. And what value did you get?
27.
27 units. Okay. So did I just find the location of the force now? Yeah, I found the perpendicular distance. But they also want us to draw the free body diagram. So here's my free body diagram. We're doing it all about what point O? So here's point O.
Don't is it okay if you didn't draw the wall, but just...
Yeah, if you just drew the bar, it's fine. Okay, so everybody put their right hands in the direction of the force. Okay, and did you even think about checking? You know how in statics we always do checks? Look at this value up here. It's a positive x value and a positive y value. And let's look at the forces. Does it make sense that the resultant force is a positive x? Yeah? How about the resultant y? Should it be a positive? Yeah, we're looking at a 200 cosine 30 going up, 300 cosine 45 going up, and then we have a 250, it's a smaller, right? If it's closer to the x, does it have a larger x or a larger y component? If it's closer, 30 degrees as opposed to 60, if it's closer to the x, does it have a larger or smaller x component? Larger x component. So the y is also a smaller number, and it's so we're looking at that, and a visual check works out. Which way is our moment spinning about point O? Positive or negative? Positive. Let me see the spin. So you know the force is going in this direction, right? Positive x and positive y. And you know it's creating a positive spin about the O. So where is this force? Is the force to the right of O, or is the force to the left of O? To the right of O. So this is wrong, right? Because this would create what kind of moment about O? Negative. So here's my perpendicular distance. 27 inches. That's my perpendicular distance. And here's my force. Okay? Some of you, I'm guessing, might have found an X value and a Y value. I'll look at that, just because I know in the past what people have done. But equivalent system problems are a little bit uncomfortable for people, so that's why I wanted to make sure that I gave the one that's the most uncomfortable. Malcolm? So you guys can learn from it. Malcolm?
So for force location systems, you don't need the direction of the distance. You just need the distance.
I think I understand your question. It's a two-dimensional problem. So since it's a two-dimensional problem, that's all I need is this perpendicular distance. I don't need the x and the y component of that distance. However, if it was a 3D problem, some of the problems in the homework were 3D, right? And all the forces are going up or down in the z direction. Then how many distances do you need?
3.
Okay, so we have a plate. We have a plate, and we have all these forces on the plate. And all these forces, I'm not as good as that guy who could balance things. Get it? You have forces going up, right? And this is in the z. Does a force in the z create a moment about the z? No, but what does it create a moment about?
X and Y.
The x and y. So I need to have a perpendicular distance to both the x and the y direction. We probably had about 4 problems in 3.
I noticed that your distance has an arrow on it. Does that matter?
No, sorry.
Okay.
I shouldn't have put an arrow. It's supposed to be a dimension, but I should have just put a line.
Okay.
Sorry. Yeah, stand on. Ethan.
Why do you not need the direction? Because it looks like you would need one.
That's all I'm asking you for is the perpendicular. It's a good question. I'm only asking you for the perpendicular distance from the point that I'm trying to find the moment about to the force, so I don't need an arrow. But, I mean, if you wanted to put an arrow, I guess it would be best to put it that way because it's an R cross F.
So this diagram doesn't make any sense to me. Because, you know, you've got your right angle, but why is it positioned like that?
Why is what position like what? Like why is the F? So there's a
why
couple of
is the F
questions.
in that direction? Why is the perpendicular distance in that direction? When if there's no relevant angle, it could be in any. It could be drawn anyway.
Okay, let's start. I just don't understand your question, so let's start from the beginning. Do you agree with this force direction?
I don't know. I don't know what the angle is.
Okay. Okay, so that, I mean, you're right. I think I'm screwing up my own rule, right? I always tell you that in a free body diagram you have to show the force and you have to show the direction, right? And I didn't show you any angle, and I didn't show you any distances yet, so I need to show you that. So we could, if you want, I'm going to just put,
It's like a 20-something angle, I think.
Yeah.
did you calculate theta x and theta y?
Yeah.
All right, what's theta x and theta y?
Like 27.1 or something.
And what about theta z?
26.2.
26.2,
And 63.7.
63.8. Okay, so, Ethan, I'm sorry, I didn't put the angle in.
I mean, because you could, you know, rotate it, or you could put
No,
the
you're
force
right,
on
you're
the
totally
opposite
right.
side of the
You should have
origin.
just taken off 2 points for my problem for nothing. Totally. Okay, a few other hands went up. Good. You all wanted to take more points off of me. Okay, now let's look at the bottom one. What did we learn about the term resultant now? What does the term resultant mean? What? Catherine? The sum of the forces. That we always knew before we got into statics, right? The resultant to us in physics was always, look at this, another statics problem.
It's a moment and a force.
It's a moment and a force, right? So when we try to find the resultant, we have to know the resultant force and the resultant moment. Did anybody write the resultant force is equal to 0?
Yeah, that's what
Okay,
it came out to.
very few
No,
of you
it
read.
was 0.000.
0.000. How many of you wrote the resultant force is 0? Okay, that's okay. All the rest of you put your hand up. I know you meant to tell me that the resultant force is 0. Because you only calculated what the resultant moment was. Is that right?
Yeah, it's
Okay.
gonna came out too.
So for the future, whenever I ask for the word resultant, you now know, and you knew last week, that the resultant is meaning what is the resultant motion on something, right? The resultant, right now I have translational motion, and now I have translational motion and rotational motion. Right? So whenever I ask for resultant, I want to know the resultant force and the resultant moment. If you only write resultant moment, I'll assume the resultant force is 0, but it's best to write both. So the resultant force is 0. Now, whenever we calculate resultant moments, and we have a 3D problem or a 2D problem, what do we look? What do we look, when we look at those forces, what are we looking for? I think we're up to Brandon. Brandon.
Couples?
See if there's any couples in there. Why? Why do we want to spot the couples?
Makes it easier.
Makes it easier to do calculations. So do we have any couples here?
Yeah.
What do we have, Brandon?
3 of them, right?
We have 3 of them.
125, 100.
We have a 100-pound couple. We have my glasses on. 125 and a 150. So, Ivan, pick one of the couples and tell me what the moment is.
150, and
Okay, let's do the 150.
that's in the negative direction.
Okay, I'm not going to put the sign on for it.
And
You
9
might be really quick at doing
Times
signs,
9.
but I like to do the math first.
times 9.
150 times 9, the perpendicular distance, remember this is absolute value. And now tell me if it's positive or negative.
Negative.
Negative, and in what direction?
The X.
Try again.
No. Hold on. In the Y.
How's it spinning?
Like this.
The force is going into the board and coming out of the board. It's spinning around what axis?
The Y.
The y-axis. Okay, let's do the next one. Arturo, which one do you want to do, 125 or 100?
125,
125. So it's 125 times what?
16,
16. Positive or negative?
positive. No, negative, sorry.
Okay,
Negative.
negative, and in what direction?
Z direction.
Okay, right. In Z. So everybody look at that. The 125 is coming out here, and it's going around here. So it's spinning around what axis? Everyone? Z. It's coming out here, it's spinning around the Z-axis, and it's spinning around the Z-axis in the negative Z. Okay, how about the next one? Hector?
So 100,
100 times
16.
16? Sound positive about that. 16, right?
Yeah.
Good. Positive or negative? What axis first? The 100. It's going up and coming down.
The Y,
The Y. Positive or negative?
negative.
Negative. And what units are we looking at? Inch pound. So the resultant moment is whatever that value comes out to be. So it looks like there's nothing in the I, there's a value in the J, and there's a value in the K, and the units are inch pound. Matt?
How would you word it if you were looking for the magnitude of the resultant? Because I was confused between whether you wanted it in vector form or
Oh,
the
is it,
magnitude.
I would.
Oh, it's right
Yeah.
there.
It says express it in vector form. So if I don't tell you how I want you to express it, what are the 2 options you have? So what are the 2 options you have in expressing a moment? Vector form or magnitude and direction angles. And it's a 3D problem, so how many direction angles do I need? 3. What are they?
Theta X.
Theta X,
Y.
theta Y,
Theta Z.
theta Z. I'm passing around the
Take a
attendance.
walk. That really messed me up. It was molded.
Okay, there was a sheet up here that everybody needed to pick up, pull this out, as well as pulling out the packet we looked at it Thursday. And open the box of connections.